All right, so welcome to the UWECE Colloquium, and it is my distinguished pleasure to introduce my dear colleague Aruna Balasubramanian from Stony Brook University. She is an associate professor at Stony Brook University. She received her PhD at UMass Amherst, and she did her postdoc here at University of Washington. Her current work consists of improving quality of life and equitable access to internet applications, improving the usability, accessibility, and privacy of mobile systems, and sustainable NLP. She has won several awards, such as the UBCOM Best Paper Award, Computing Innovation Fellowship, VMware Early Career Awards, Applied Networking Prize, as well as she's what we call in our SIGMobile community a rock star. She's also passionate about improving diversity in computer science and leads the diversity committee at Stony Brook, as well as is the faculty advisor of Women in CS and Women in PhD groups at Stony Brook. Today, she will be talking to us on how to do systems research for user-facing problems. Let me welcome Aruna and hand over the mic to her.
Thank you. Thank you, Akshay. I've known Akshay since he was a PhD student. It's been great to come back to UW. I was here between 2011 and end of 2014 and had a wonderful time here. So I'm always happy to be back here. Today I'm going to talk about, and everybody can hear me fine in the back? Okay. If I actually bring this accidentally close and it becomes loud, please let me know, okay? All right. So what I'm going to talk about today is systems research for user-facing problems. And this is a more from the, when I say systems, I mean from the more computer science systems point of view, mobile systems, operating systems, and that sort of stuff. So let's see. So traditionally, systems research focus has been on these metrics such as how do I make latency smaller, how do I make my bandwidth or throughput higher, how do I do reliability, and so on and so forth. But there are many, many other user-facing metrics that users really care about, the end users really care about. And so, for example, equitable access. Am I getting internet access at all places equally well as in developed regions, for example? Sustainability, QoE, so on. So our lab has been working on how do I make systems research improve some of these user-facing metrics. How do I measure these metrics? How do I even define these metrics? And how do I improve performance? And so today I'll talk about a couple of these, touching just a few of these. I won't be able to talk about all of them. But the general theme of everything I'll talk about today is the first one is generalizability. So the question obviously is, why should I use systems research to improve user-facing problems? And my take on this is that many of these system design and system ideas are useful in terms of scalability and generalizability, and so that's what you bring to the table, essentially. So take the example of accessibility, all right? Accessibility means how do I make computing resources accessible to people who have disabilities? So there has been a huge, rich amount of work in the HCI community on accessibility and understanding users and problems and so on and so forth. But I think what systems brings to this table is how can I now build accessible technology that works across applications, that works for different people with different kinds of accessibility. So generalizability is a general theme of much of the things I'm going to talk about today. But then the mirror image of that is interdisciplinarity. So this means that you do have to work with the experts, domain experts in all of these different areas to understand what they've done so far, what are the problems they're facing, and see how systems research can contribute to this whole issue. And that's what, so it's very key to be able to work with people in different domains so that you can actually figure out how you can help and how you can augment. So the first topic would be on accessibility. This is actually close to my heart. I've just been working on this for the last 3 years or so. In fact, when I was here at UW, I used to talk to Richard Ladner a lot. I don't know if you know him. He's in computer science, and he does a lot of accessibility research, and I was always fascinated by it. But at that time, I didn't know how I can use systems research to improve accessibility, so I didn't do much. But then since then, I've gotten into it. Now I think that there is an angle for systems people to do something in this space. And like I said, accessibility is making computing technologies usable for people with disabilities. So according to CDC, 1 in 4 in the US have some kind of disability. And there has been a lot of studies in the HCI accessibility community about how smartphone interactions is simply not accessible to people with different kinds of disability. And by the way, feel free to stop me in the middle and ask questions if you want. So for example, let's say that so for the blind user population, the way that you interact with your phone is that you have to do some touch screen on the phone, you swipe right, swipe left, and so on. Often you have to use both hands, and that's hard when you're holding a cane or a guide dog, for example, right? This is just one of the many, many different accessibility problems that users face. If you have Parkinson's disease, then you do not have the fine motor skills needed to actually interact with the application. So these are some of the problems, and this is well known and this is well studied. So the question that I wanted to know is, can I use alternate, what I'm calling contactless gestures to improve accessibility? And let me tell you what I mean by a contactless gesture. What I essentially mean is if I can move my arms, for example, right, or move my head, and somehow I can capture that. And so, for example, an arm movement is not as much, I don't need fine motor skills to do that. Right? And so can I use this to replace whatever interaction that you do right now on your smartphone screen? And I should mention before I move on that voice is another alternative that people often use for interaction. It's not just the touchscreen gesture. But the voice itself has many problems. For example, voice is mostly used for what I call text entry. That is, you're sending an email, for example, or you're typing a message, right? Not so much to do content searching kind of things. But also voice has other issues. It's privacy problems, it doesn't work all the time, it doesn't work outdoors, and so on. So anyway, so the idea was, can I use contactless gestures? And why do I think we can use contactless gestures? Because there are lots of wearable devices that people use these days. You have smart watches, you have smart earbuds, and they all come with different kinds of sensors. So the most common sensor that most of these come with is called IMU. I'm sure you've all heard of IMU. It's gyroscope, accelerometer, magnetometer. It tells you, it can capture linear motion, it can capture rotational motion, it can capture like orientation and so on. There are also other things like microphones. So the question is, can I use some of these to recognize these gestures, what I call the contactless gestures, hand movements, head movements? The other enabling technology, and the reason why I think this is possible, is virtualization. So we've done a bunch of work in our lab on virtualization, where you're basically replacing one resource with another resource, right? That's essentially what virtualization does. For example, if I'm doing, let's say, UI virtualization, what I'm going to do is I have the screen, I have some information on the screen. Maybe I want to virtualize this and show it on my watch instead, so that I don't have to take my phone out. I can just use my watch and interact with the application. That's what I mean by virtualization. So here the idea was, can I virtualize the input, right? So the input is how I interact with an application. Maybe I can virtualize that. In fact, the reason we thought of this is because we had done another project called Doc Reader that virtualized the keyboard for blind users, and that for energy reasons, and it worked very well. So could we do this? So this is why I started this project. There were these two ideas floating around. I thought maybe these could be combined in certain ways to provide accessibility. And so the overall vision is that if you're a user who has different kinds of accessibility problems, I want to be able to use contactless gestures to interact with any application on my smartphone, right? That's the key here. I don't want to write a new application for you to work with. It has to work with applications. Right now, at least for this talk, I am focusing on touchscreen interactions on the smartphone, right? So, and we've been working on other things since, but this talk, I'm just talking about touchscreen. And I'm hoping that I can do some virtualization and gesture recognition. I'll tell you why this is not as simple as it sounds, but that was the big idea back then, that this is what I wanted to do. Well, we talked to I actually talked to the web accessibility officer at Stony Brook, who's blind, And I told him this grand vision of mine, and he said, look, make this work for one target population. Make it work for a small number of gestures. Like, show me that this works before this grand vision. And so that's what I ended up doing. And that's what this talk is going to be about. So I'm going to focus on blind users and use contactless gestures that you can make with your arms. That is, you can move your arms around. And essentially, I want to know, can I provide accessibility, that is, allow users to access smartphone applications using these alternate gestures. Okay? All right. So what we started, as any reasonable person would do, is to actually have a formative study with blind users. And I should mention that I had done some work previously, like I said, the doc reader work. And so I had talked to users in New York. There is an institute where you can go and you can do user studies there. And I had some sense for this is something that is useful for them, which is why I started this project. But anyway, we did a formative study to be more quantitative about this. Say, to figure out whether this is useful, contactless gestures, and how blind users perform gestures, what their preferences are, what kind of gestures do they like to do, and so on. So that was a study. And I'm not going to be able to talk a lot about the study. There's a ton of things we learned and wrote a whole paper about it. But I'm just going to summarize our finding from the study, and which basically informs the rest of the work. So the first finding is that all of the participants, oh, by the way, of the participants, I think 90% of them owned either a smartwatch or a smart earbud. Right? So this is not something that they don't have. They all had some problems with using touchscreen. And they were very excited about the idea of using a smartwatch to do gestures. By the way, at this point, they don't really know what it means to work, what it means to use an alternate gesture. We just sort of provided them this idea. And so I'll just tell you a few quotes. So one of them said, in public, I don't feel comfortable taking my phone out. I don't want to draw attention. This is New York City, so you can imagine. And one of the reasons for this is because the way that most blind users interact with their phones is that they have to use these touchscreen gestures, but they can't see what's on the screen. So almost all phones come with what is some kind of a talk-back like system that will read out whatever is there on your screen. And so essentially, you could put your phone in the pocket, have a earbud, and listen to what is going on. Don't have to take the phone out at all if you can use these contactless gestures, right? Which is a huge plus. Another one said, gives me the confidence not to take out the phone. I just said that. Everyone carries a watch. If I wave it around, nobody will know. And so on. And they have said many other, they were actually very excited about this. And one thing I should mention is that all of the users, the participants we worked with were extremely tech savvy. And so they used their phone a lot. In fact, all of them carried a battery pack with them because in case their phones run out of battery, right? This was that important to them. The other interesting thing is that everybody had a unique preference for what gestures they wanted to use, even with the hand gestures. Like some of them liked wrist gestures, some of them preferred some other gestures, and so on. And this is really key, especially when you're working with this target population, and not just blind users, but people with disability in general, is that they can be of different form, which means that the kinds of gestures they want to use would be different. Not only that, they also had a preference on how they wanted to map the gesture. So for example, let's say that I'm going to swipe right on the screen, right? And I want to know, hey, instead of swiping right, what gesture do you want to use? One of them would say, I want to move my arm to the right. One of them would say, I want to move my wrist to the right. They had different opinions about what kinds of gestures they wanted to use, again, based on their own preferences. And this finding will become important later. I'll tell you why. Essentially, what we want to do is to provide a flexible way in which you can map gestures for different users, right? The second finding, and this is more important, is that blind participants show high variance when they perform these gestures. So what I'm showing on screen right now is essentially the gyroscope data. Gyroscope is a sensor that does rotational motion. And for two different users, both of them are doing wrist rotation. And you can see just visually that they look pretty different. In fact, we did the same study with sighted users and found that if you just, I'm not going to go into the details, but if you can do DTW-like techniques to figure out the distance between these gestures, the gestures between sighted users are pretty close. The distance between blind users are actually pretty far. So it's not only that the blind users do gestures differently from sighted users, they do gestures differently from each other. Right? And we actually dug a little bit deeper into this. I'm not going to go into too much detail, but it turns out it's because when you ask a blind person to do a gesture, they don't get a visual feedback of what the gesture is, right? So I say, hey, move your hand like this. If you're sighted, you're going to look at me and do the exact same thing, but that's not true for the blind users. So anyway, so why is this important? Because all of these techniques that do gesture recognition using IMU use thousands and thousands of training data from sighted users. That's not going to work, right here. Anyway, so that's the user study. So our goals now are we wanted to build a gesture recognition system that can recognize some simple gestures, about 8 in the beginning, and I'll talk a little bit about more complex gestures later. And we wanted to figure out how I can integrate these gestures with an application without making any changes to the application. Right? I want it to be 0 effort. So those are the 2 main goals. So let me first talk about the gesture recognition. I don't know how many of you work with IMU gesture. Anybody here has worked with IMU gesture recognition? Okay. So maybe this won't be that exciting to this audience, but literally there are tens of papers on IMU gesture recognition. In fact, when I started this work, I was more interested in the virtualization part of the project. I assumed the gesture recognition part is solved. Turns out that that's not the case. What I'm showing you is the 20 of the, state-of-the-art papers. And they all have one or more issues. And by the way, just to be clear, an IMU gesture recognition essentially means that you're going to track the accelerometer, the gyroscope, and the magnetometer, figure out what the linear motion is, figure out what the orientation is, and your rotational motion is, and then somehow combine all of this and say, this is the gesture you made. You moved this way, or you drew a square, or whatever. So the problem is that you either need a lot of training data. I told you that's hard. Or you can use per user training or personalized training, and even for that you need about 600 samples. Or it doesn't work in real time. Right? I'm just going to show you one example. For example, TapNet is this work that used 130,000 training data from sighted users. Right? I'm not going to get that amount. Muse, for example, it builds a point cloud to track you. But that is not, you can't do that in real time. So what we wanted to do is we wanted to do IMU-based gesture recognition in real time without large-scale training. And there are 2 insights to this work. The first is that, so we had to combine all of the data together, the magnetometer, accelerometer, gyroscope. What we figured out is that we don't actually, first of all, doing that sensor fusion is expensive. Right? That's one of the reasons why you can't do these in real time. We figured out that we don't really need this. Because even, especially for the kinds of gestures where we are looking at, there is a rotational aspect to it, so we could just use the gyroscope. Magnetometer is actually usually really bad when there's a lot of pollution, like ferromagnetic material all over the place. And at least for the blind user population, the accelerometer was not very useful. Right? What I'm showing on the screen here, the A, B, and C are the accelerometer data for the wrist rotation gesture. D and F are the gyroscope data. The D and F look different, but less so than the accelerometers. Right? So that was the first thing. And one problem, if you work with gyroscope, is that it tends to drift a lot. And that's why people use accelerometer. But because our gestures were short, we were able to get away with that. So the next insight was, so what we essentially wanted to do is just use gyroscope, but see if we can identify an invariant micro movement that is common across these gestures. I told you that the gestures were itself very different, but it's possible that maybe there's a small micro movement that is common. Because the way that gestures work is that there is a pre-phase where you get ready to do the gesture, then you do the gesture, and then there's a post phase where you sort of go out of this gesture, right? And so what we noticed was that So this is again, I'm showing the gyroscope significant axis for 5 users, all doing the same gesture. And at first glance, they all look very different. But it turns out that actually there is a nucleus that is pretty similar across these gestures. And we found this to be true for all of these simple gestures. And so now our life becomes a bit simple. All we have to do is to figure out how to extract this nucleus, and then we'll be able to do some simple classification, which we ended up doing. And you could just do change in energy, for example, and that gives you the start and stop of the nucleus. I'm just going to do a quick aside that, for complex gestures, this didn't quite work. For example, if you do a square, this is actually what the 5 gestures look like for five different users, and you can see that actually they are all over the place. But what we could do then is to take all 3 axes of the gyroscope and look at it in 3D. Again, this is the 3D nucleus for 2 different users. And here, actually, they look reasonably similar, right? And I'm not talking about some of the complexity here. There are things like you may not have the same orientation. You might be in different planes. But you can essentially use these graphics ideas like curvature, torsion. These are all invariant across any shape. And so you could use those to recognize these gestures. So essentially, our takeaway is that gyroscope is sufficient to recognize short arm and wrist gestures without requiring training data. OK, so now the question is, OK, I can recognize a gesture. How do I replace the smartphone application to now start using this new gesture? To appreciate why this is difficult, let's take an example. OK. So let's say I have an application, and this application works with a swipe up gesture to do some task. And it might do other things as well, but just take one example. For example, if I swipe up, it might show me who the artist is, let's say. That's what the application does. So the way that today's smartphone applications are written is it's actually monolithic. That is, the logic and the input are all intertwined into one program. So now if I want to, say, use a swipe right gesture to do the same thing, what should I do? I should rewrite the application, say, now if I have to trigger this, this is what you have to do. Imagine now different people want to use different gestures to interact with the same application. You have to write a different application, you have to rewrite the application. Just for one application, you have to rewrite it over and over again. This would never scale. In fact, most of the work in the accessibility community that talks about alternate gestures, the way they get around this problem is to just write an application that will work for that alternate gesture. But if you now want people to use any application with these alternate gestures, this will not work, right? We have to figure out a way to solve this. So, this is actually what I was initially interested in. The gesture recognition was I just didn't realize that it didn't work. But is that we want to decouple your application logic from the input, because I told you that programmatically it's written in the same way, but virtually I want to decouple the two. And so what I would do is that I would decouple it in such a way that I can use any other gesture. I have to figure out which gesture maps to which input. Let's talk about that problem later. But once I know that this gesture maps to this other input, I should be able to use any other gesture to trigger that. And the way that we do this decoupling, and I'm not going to go too much into this, is a little bit in the weeds, but I'll just give you a very high-level idea of how this works. And so usually the way that most mobile operating systems work is that there is a single conduit to the application to get all sensor data. And this is not just input, any sensor data. So the way that you have these hardware sensors, they go through the sensor service provides the sensor data to the app. And what we want to do is to create a virtual sensor and a virtual sensor service. And so let's say that I am going to replace my swipe up with a hand up, right? What I will do is I'll first figure out that I will recognize this as a hand up gesture. then I will use a tool called record and replay, and I'll talk about it in a second, where every time I do this hand up gesture, I will replay the swipe up gesture and provide that to the application. The application would think that this was generated by a user and just continue to work, right? I am skipping over a lot of complexities here about how you would build this record and replay tool. For example, if for simple gestures, maybe you can do this replay, but from other inputs, maybe this would be hard, and so, but you could make this work. So once you do this decoupling, of course, the other thing is, how do I know what gesture to map to what other gesture? Remember that users have unique preferences in how they want to use these gestures. And so this is something called, we assume that there's a simple meta program. This is not a program, this is just a text. Okay, map this gesture to these other gestures, like an XML, and you could just look at this XML. And what we did, at least for our study, is we created this meta program, and then we created a user interface. So if a user does not want that mapping, they wanted to change it, they can just change the mapping. Right? Okay. So essentially, what we can get with Accessware is that you can have any application work with an alternate contactless gesture without making any changes to the application. The application remains the same. This means that you can actually deploy this for many, many applications, and it will scale well. I'm not going to talk about too much of the evaluation. I just wanted to show one, which is gesture recognition accuracy. We did this again with 9 blind users, and we asked them to do various tasks so that it's not that I'm saying, hey, like, turn your wrist and see whether I can recognize turned wrist. Like, that's a little silly. What we wanted them to do is to say, okay, do this task which will involve many, many gestures that they have to remember which gesture, and they had written their meta program to do the mapping, and so they would do these tasks, and we would record what they do during the task and see what the accuracy was. And got a 92% accuracy. It outperformed some of the state-of-the-art. I'm not going to go into the details, but it does so without requiring any training data. Okay. And we also asked them for qualitative feedback. Obviously, I did this work with a lot of HCI people, where this is one of their main things. And they found this to be, one of our worry was that maybe the mental stress of remembering what gesture means what, and then doing the task may be hard. Turned out it wasn't hard. And so we evaluated other things like end-to-end latency. It was actually under 50 milliseconds and so on. So coming back to our vision, what do we want to do? We actually wanted to continue working in this space. We wanted to do more. We're working right now with patients who have Parkinson's, who have a completely different set of problems than users who have vision impairments. And so the idea is to actually get as close to this vision as possible. All right, so I'm going to pause for a second to drink some water. If anybody has any questions, you can ask.
So I have one question. So how would you know the location where you're swiping up?
That's a very good question. So this is why I said this is have to be a little bit in the weeds, right? So for some of them, most of these gestures, it doesn't matter where you are, so you can do that. But if you have a specific location, like there's a button, right? So what we do is that these buttons they form a UI tree. You can access that UI tree and figure out exactly where it is, and you can press it. Yeah, so there's a little bit of engineering involved there. Yes?
So how did you run into problems where there wasn't an intent for like an action and you misrecognized the gesture?
That's a very good question. So we actually did these, I missed one thing. So that is a problem, right? Because maybe I'm moving my arms to do something else, and it recognized this as a gesture and started doing random things. So we have a lock gesture for that, right? So you can lock and unlock. And if you lock, that means it not going to do anything. If you unlock, it'll start doing things. And then what we did was gave these phones to users for 5 hours. And we said, there was any false positives? And actually, there was no false positives for 4 of the 5 users. For the 5th one, there's lots of false positives. Not lots, maybe 2 an hour, and that's because they were doing dishes, and apparently for some reason it got unlocked. Yeah.
Is there like a range limitation on, is there like a certain distance away from the smartphone?
Oh, yes, it does matter because we are using Bluetooth at this point, right? So yeah, see, I'm assuming that the smartphone is in my pocket, my watch is here. Yeah, absolutely. And right now we are doing with earbuds, right, to do motions like this. Obviously there it will be close by. Okay. So the next topic would be on privacy and sustainability. I think I have time, we'll see. And it'll become clear why I'm putting privacy and sustainability together. By the way, this is a completely different topic. This is, so we started this work because there are lots of intelligent assistant systems out there. It'll do things like recommend movies for you, recommend what clothes you will be interested in wearing, to answering questions, to have these intelligent assistants like Alexa and so on. And they provide you a really good service. The problem is privacy, right? Somebody has all of your information and they're figuring out a model about you. And this is the world we all live in right now, and seemingly comfortable about it. So the question we asked, and this was back in 2018. Oh. Okay. The question we asked was, so take one application, question answering. Can I do this on device, okay, without the internet? So for example, let's say that I've looked at some websites, there's some social media, I have some information about let's say some disease I have emailed from my doctor, and now I want to ask a question about, hey, what drug should I be taking based on all of this information, right? It's better, it would be nice from the privacy point of view if I can just ask this question locally. I have all of this information on my phone, and I get an answer to this. Well, it will be nice. The reason this is not possible is because all of these question answering applications work on using deep learning, and deep learning simply does not work on the mobile. By the way, I'm talking about 2018. Now there are more serious problems than the 2018, and I'll get to that in a second, okay? So when we did this back in, well, we published the first paper in 19, but we started this in 18. The problem is that the models don't fit in memory. You can't just load this on the phone, and they're also extremely slow, right? For example, the models would take 80 seconds to answer a single question. Even if I figure out how to load this on the phone, it won't even load on memory. So to explain to you why this is the case, let me give you a quick background on how QA works. So what you do is you have some question, you get a bunch of documents that you think has the answer, and then you do something called embeddings, where for every word, and the NLP people call this token, you convert it to an n-dimensional vector, such that if two vectors are close to each other, words have similar meanings. For example, queen and king will be close in this vector space. Okay? So this embedding has a large vocabulary, because if you want to answer questions, you need a large vocabulary, and it can take easily about 2 gigabytes of memory. And it has to be loaded in memory because you have to keep looking at this. And then once you have this embedding, what you do is that you have this model itself. The model also has memory issues, right? But apart from that, from the compute point of view, what these models do is that they take these embeddings so they'll take all the documents, they'll take your question, they'll convert it to the embedding space, which means that for every word, you'll convert it to this vector. And then you will start providing more and better representation of that vector based on context, right? What other words does it appear with? Is one context. And so you keep doing this over many layers. You finally have a really good representation of these words, and then you can essentially say which sentence gives you the answer to the query. So that's how this works. And so the embedding is memory intensive, the neural encoding is compute intensive. And this is how it worked in 2018. This is how it works today with GPT-4, GPT-3, I don't know how GPT-4 works. But yeah, right? So let me first look at the compute part. I'll talk about the memory in a bit. How are we going to design ways in which I can run these more efficiently on the phone. The biggest problem is that these models keep changing. If I design an approach that works for one model, in 2 months there's going to be a new model that's going to be changed. And I had this notion back then that I was working with an NLP, actually NLP researcher who's also my husband, who's also a postdoc at UW, incidentally. But I said, you know what, screw this, let's design our own QA model for the phone. And he cautioned me against it, and I'm happy he did that, because he said, look, the field is going to keep improving its accuracy, and you're going to be stuck with an old model, and nobody's going to use this. It doesn't work. So we had 2018 state of the art, and this is what happened in 2021. I gave a talk where I showed this. There are models with increasing accuracy and increasing number of parameters, starting from 94 million to 11 billion. And now, 11 billion sounds like a joke, right? We have 783 billion parameters in GPT-3 and GPT-4, God knows how many. So these models keep changing. So we'll have to design, our goal was to design systems and memory optimizations that actually generalize across these QA models. So I'm not going to take the QA model and figure out how am I going to make this efficient. What I'm going to do is to say, what is the general idea of a QA model? What does it do? And where are the bottlenecks, and how can I solve that? And I'm not going to have time to talk about all of these generalized optimizations we did. But what I will do is to talk about one idea. Okay? So the idea we had was, remember I told you about the neural encoding. So for every document and question, I have to encode this to provide more context. So what we found out, this was again 2018 models, is that we have these models. We use something called LSTM, which is the model du jour at that time. And we found that the question encoding and the document encoding, they are separate. They are not dependent on each other, right? This means that, and documents are much larger than question. Encoding the question is not that hard. So a very simple trick, this is a classic systems trick, is I'm going to just encode these documents beforehand and store them in a cache, and I will just access this cache when I need to at runtime. Of course, what I'm doing is I am trading off compute for storage, but it's okay. On phone, storage is not a big deal. So this was an idea, and actually this worked out quite well. But then, I don't know how many of you are following NLP. There was this paper, attention is all you need. They changed everything. The way that so I'm not going to go into the details of how the neural encoding itself. Essentially, this is more computationally intensive because the way that you did this encoding in the previous version is that you would look at this word and see what the previous encoding was and encode this based on that. Whereas in attention, you take every word and figure out for every other word what is the context, right? So there's n square amount of computation you need to do. But the more important problem from our point of view was that here the question and the documents were encoded together, right? So we lose this whole dependency thing that we had before where I said, oh, they are not dependent, I can just encode this separately. So this looked like this is a lost cause, which was sad because actually this is interesting. We submitted this paper to MobiSys, and 2 days later BERT came out. Right? And then we saw that actually what we did didn't work for that model, which was disappointing because the whole point of our work was I wanted to be able to generalize. Luckily for us, we did manage to use that idea here as well. So what we do is we actually say, okay, I know that the question and NLP people call this context. It's basically documents. So the question and the documents are encoded separately or together. But what if I encode them separately for the first k layers, and then I would store them separately and do offline analysis and whatnot and save some compute. But then I encode them together, and then I have to use some tricks like distillation, which I'm not going to get into, to improve the accuracy. And that worked. Right? So this means that for the first k layers, I can do offline neural encoding, which saves me some time, and accuracy doesn't drop because I do other tricks on top. And in fact, this idea worked later, and I'm not going to talk about that because we started doing some work on visual question answering. Because blind users, you do a lot of visual question answering. Can we do that on the mobile? Turned out this idea works there as well. And so the takeaway here essentially is that generalizable systems memory optimizations can apply to diverse kinds of models. You don't have to do this one optimization for a given model. So for example, for memory, what we do is very simple, again, simple system ideas. We do key value store. We store this as the embedding as a key value store in storage instead of memory so that it's easy for me to load. We also do these tricks like partially load the model and keep swapping it back and forth so you can load them. And so what happened with this is that the optimizations provided significant gains. This is actually for the orange lines or the time it takes for models to answer, and the green lines are how much we were able to reduce it. And there was a 13x speed up. But this is not only for the mobile, right? Now, these big models that are out there, it's not just a problem of privacy anymore. It's not a problem of can I run this on the mobile device. Even to run on a GPU, it takes you a long time and a lot of money. The cost is high. You want to increase throughput. So in fact, what we show is for these bigger models, you don't see that much improvement on the mobile. But if I run this on a GPU, for example, I can actually get a much better throughput, 3x throughput. So that means process more queries, which is more money for companies, right? And the interesting thing here is that when we were working on privacy, nobody really cared about it. But now efficient NLP is very much in vogue because it's a question of money, right? So in fact, there was this paper, we contributed to this as well. This is a Darkstool seminar run by NLP people on how do I do efficient NLP. They've finally woken up to say that, yes, we need to do this. And some of our systems people were involved in this as well. Okay. So the last part, and I should wrap up in 5 minutes on this, is that since now these models have become bigger and bigger, we've started looking at the energy impact of these models. Right? I'm going to show you, this is a 2019 seminal paper by Emma Struble and others at UMass that showed the carbon emission of various different things. Training an NLP model, the carbon emission is 2 orders of magnitude more than an airplane traveling from New York City to San Francisco. And this is becoming a huge issue these days. And by the way, this was done in 2019, so they had to make a lot of assumptions, which, like, for example, what kinds of hardware is it trained and so on. And so there's a little bit of controversy about this paper today because maybe you have to take into account hardware. But actually, the problem remains. Sustainability is an issue. So what we wanted to do was to say, the first step towards sustainability, we've been doing more things since, but this year I'll talk about the first step, which is, can I even know how much energy a model will take? Right? And so then, if I do know that, can I then say, if I change the model in a certain way, what will be the energy savings? Can I do that today? So when we started looking at this, we looked at what models were used at that time to do energy prediction for NLP models. The x-axis here are 4 different NLP models. The y-axis is the error. There is up to 65% error in how the energy models. And when we looked closely into it, it turned out that every problem that the SIGMOBIL community faced on what you should not be doing when you do energy prediction was what this model was doing. And this is not their fault. Like, these are NLP people. They don't have to know how to model energy. But anyway, my point is, here is where I think systems research would come in handy. We've been doing this work. We know how to model energy. So I decided that we wanted to do this. And we wanted to design an interpretable and generalizable energy model. And the idea was to do what I'm calling divide and conquer. Okay? And this is an idea that I'd used to do energy modeling in 2 of my other papers for some other systems. So we basically said, okay, can I use the same idea? So essentially, there's a model. I'm going to break it down. Okay? And I'm going to actually see whether I can predict the energy of the lowermost layer and then build up and find the energy of the higher layers. And the nice thing about that is, and let me show you an example. So let's see, I'm going to do a multi-level energy prediction. So what I would do in the first step is I would do the energy, the way that I'm going to do this abstraction is the lowest layers will be machine learning primitives. These machine learning primitives are the same for every model, which means if I now know the energy prediction of those, I can use that same prediction to compose the energy for a different model, right? So this gives me generalizability. And then I'm going to run a multi-level predictor that can then predict the energy for every layer up until all the way to the end. But this also gives you interpretability, because now not only do I know the energy of that model, but also every single component, which means I can compose this differently and do what-if analysis and show what will happen if, let's say, from 16 layers I went to 8 layers, right? How much energy will I save? So we've been doing a bunch of work here. First, the errors are much lower. In this case, this is again with the state-of-the-art, and we called our system Irene. I've actually forgotten what it stands for at this point, but under 7%. We also built this demo visualization tool. You can load a model and specify parameters. It will tell you how much energy it will take. Okay. So the main takeaways from all of this work is that improving user-facing metrics is as important, if not more important, than quality of service metrics. So we should be doing systems research in this space. But of course, the key is doing interdisciplinary research, because you have to understand the problem very deeply, right? You can't just do low-hanging fruits here. Some of my faculty collaborators, Niranjan for the NLP work, Ivy and Shaojan. Actually, Nick and Niranjan for the NLP work, Ivy and Shaojan for the HCI work. And of course, all of this is thanks to my students. These are all the students I've had in the lab, which is all excellent. And I also believe in actually creating a culture where I put people first. So we've always had fun things to do as a lab. That's actually a hot pot that my students prepared. So because, it's, at the end of the day, it's all about the people. Thank you.
Any questions? Yeah. Maybe I'll start with that. And by the way, the microphone is capturing all our voice. So how would you combine your NLP work, given that GPT is becoming more and more common, and combine it with your other work, which deals with like building these accessibility technologies? How would you combine both of your expertise together?
I think, so there has been some, I don't know about GPT-3, but one thing that we've been working on is visual question answering. Right? Blind users tend to use these visual question answering a lot. So basically, they'll take a picture of something, they say what it is. But the way that they have to do today is they have to send it to the cloud. Right? And the cloud would say, okay, this is what it is. And that is a huge privacy violation, because the cloud now knows where I am and what my surrounding is and whatnot. And so we showed how you can use some of the ideas that I presented to do visual question answering completely on the phone. Right? With like a 20x speed up. So, but yeah.
Maybe I'll ask another one. So when you were doing this NLP optimization, there's an inherent reason why they require you to run these models in the cloud, because they can then use your data to train better and better models.
Yeah.
So what incentives do these big companies have on enabling you to run these models on your phone? Because they want your data, right? That's the thing they're saying.
Yeah, that's true. No, they don't have any. I think the way to do this, and many academic institutions I know at least thinking about it, if not doing it, is actually building their own. Right? Because there is, well, there might be, I'm not an NLP expert, but I don't think there's a magic sauce to this, right? It all uses attention-based transformers. The magic sauce essentially is how big is your transformer, how many attention heads do you have, how many layers do you have, and so it's not that so you could, if you have enough resources, you could recreate that. And so one idea, for example, that I think is taking a hold that I think will become big in the next few years is this distributed training model, that I have many machines, maybe across universities, and they all do a little bit, and they can all train together so that you can create the kind of things that GPT-4 can create. Yeah.
So do we have like updated energy consumptions of the new models that are coming out? You posted like 2019 results.
Right, there is a few, but not with GPT-4 because it's too new. I think GPT-3, there was some number that was ridiculous. I don't remember the number off the top of my head, but it was some ridiculous number. By the way, one of the things that's interesting is that if you talk to the Google, oh, well, this is recorded. Well, okay, it's fine. If you talk to Google, they'll claim that they're carbon neutral, okay? And they'll claim things like, oh, training is done once and it gets amortized over the many, many ways in which you're doing inference. But actually, Facebook, who said this, also the researchers had a paper that showed that that's not true because the way the training works is that you finish the training one model, you start training the next model. Because the trainings take so long that you actually have to start inferencing with a new model. So really, there's no amortizing going on at all. And so yeah.
Just a follow-up. So were those numbers like way off or were they like kind of accurate?
So the problem, I think, and this is something that we're working on, right? The problem is that apart from the training itself, there are many, many other costs that you have to do in the data center. One of them is that you buy hardware, and that hardware, you have to replace the hardware, right? So there has been this recently a spate of work, not my own, but is how do I even define how much energy is being used by a data center for training? And I think our model gives you a reasonable estimate of just the model itself, the training, the energy, but then there's other works that also are saying all these, you know, how much energy does the wear and tear take, how much, and putting all together to say this is the magic number is work that is ongoing right now.